3, 2, 1, 0.
Traveling can be a headache. There are dozens of things to remember and so many things that can go wrong. But traveling to space kicks up the difficulty settings, raising both the stakes and the price tag substantially. Just like you and I try to avoid extra bag fees, the very smart people designing rockets are always trying to minimize the mass and therefore the cost of sending stuff into space. When you forget your toothbrush on a vacation, you just get a new one. If you need a specific tool on the International Space Station, one that you didn't bring with you, you'll have to wait for a resupply mission. Or maybe you can 3D print a replacement. But what happens if astronauts are too far away for supplies to be shipped to them? And is it possible for deep space colonies to ever be completely self-sustaining? On Earth, when humans left their home countries and set out on the open seas to reach new lands, they couldn't plan for every possible necessity and future need. They had to be resourceful and adaptive. It also helped that for many early colonies, especially in the Americas, there were many indigenous peoples who had lived on and with the land for generations. These land stewards, being familiar with the land, often gave these new inhabitants guidance on how to utilize the local flora and fauna in their new home. If it wasn't for this knowledge, early colonizers likely wouldn't have been able to survive in their new home. As we look out onto the stars and make plans to visit them, parts of humanity once again aiming to become colonizers, how will we adapt to the harshness of life out there? Extending our civilization into deep space will require more than big rockets and cool spacesuits. Humans need food, water, and air to survive.
Vegetables have been grown in the ISS and consumed by astronauts, but China's Chang'e 4 mission became the first to get seeds to sprout on the moon. However, due to the harsh climatic conditions, the plants died soon after. Interestingly, researchers from the University of Melbourne in Australia have found that plants could be augmented with nanomaterials to give them new properties, such as shielding them from harmful UV rays and allowing them to use the UV rays for photosynthesis to generate energy. Each person requires about a gallon of water per day. Most of that gallon can be recycled after it passes through our bodies, which is good news for astronauts. The International Space Station has an advanced system for recycling wastewater. Used water is captured from sinks, toilets, or even condensation from the air, gets filtered, and then made available for reuse. More than 90% of the water on the space station is made available for reuse. Aside from reusing human wastewater, scientists have discovered water resources on the moon and Mars. On Earth, oxygen is available to us in the air we breathe, so we don't really think much about it. But in space, especially if we're talking about a planet without oxygen in its atmosphere, we're going to have to make other arrangements. In nuclear submarines, they operate what is known as an open loop system. Open because it's based on chemical reactions and exchanging materials with the environment outside. But on the International Space Station, where there is no external atmosphere or reservoir to exchange gases with, they operate what is known as a closed loop system. The oxygen generation system generates oxygen by breaking up water molecules into hydrogen and oxygen. Another system, the advanced closed loop system, recycles carbon dioxide into oxygen.
Even beyond those core needs, to survive in deep space, we'll need to create completely self-sustaining space colonies. To be self-sustaining, a colony will have to tackle all of the tasks that civilizations on Earth must in order to survive. Namely, manufacturing construction materials, disposing of waste, extracting resources, generating energy, and keeping the crew entertained and engaged. Keeping the crew entertained is easy. Send them up there with a few seasons of The Office and they'll be good for a few years. Or if you're me, at least 8 semesters. If a direct fusion drive becomes a reality, it might even be possible to send high-quality video out to deep space. Direct fusion drives are a nuclear fusion engine concept that produces both thrust and electric power. I mean, astronauts will probably use the high-speed data transfer rate to communicate with Earth scientists, but it's pretty cool to imagine astronauts of the future being able to send high-quality video messages or more back home. In the meantime, there are 2 libraries with books, tablets, and limited internet access on the International Space Station. One favorite pastime on the International Space Station is checking out the view and taking some pretty awesome photographs. When it comes to generating energy, hopefully by the time we're that deep out in space, we'll have super convenient and clean fusion technology. But if we don't, deep space colonies might use powerful solar technology to keep the lights on and batteries charged. When it comes to disposing of bodily waste, there are some options on the table. A few years ago, NASA ran a Space Poop Challenge, a competition to develop a spacesuit that could extract human waste, both liquid and solid, without contact. Researchers at Penn State University didn't want to miss out on the fun and poop jokes and have developed a bioreactor that can use human solid waste to grow an edible, protein-rich microbial goo. I know it sounds strange, but eating a smear of microbial goo would be a little bit like eating some Marmite or Vegemite. Most human wastewater is recycled. On the International Space Station, sweat and urine are recycled, with more than 90% of the water being available for reuse. On the ISS, other kinds of space trash are just tossed out into space, though efforts are being made to find ways to recycle more waste. When it comes to extracting resources, one of the main drivers of deep space exploration is just that. Whether they're mining key minerals from a moon or extracting frozen water from an asteroid, there's a lot of interest in finding ways to get the goods out of space rocks. Being able to extract local resources and repurpose them into construction materials or even food will be key for any long-term mission venturing out into deep space. Scientists and astronauts will have to get really good about using what they can find out there to keep missions going. Flying to and from asteroids to space-based manufacturing plants will be cheaper than flying raw materials out from Earth. Asteroids have lower gravity, and therefore lifting off with rockets requires less power and less fuel. The basic concept of in situ resource utilization is to develop products using locally available raw materials. This is true on Earth, in outer space, or even on the surface of other planets or celestial bodies. In the German fairy tale Hansel and Gretel, 2 children stumble upon a house made of gingerbread, cake, and candy. Spoiler alert, that delicious house was bait. In the real world too, food has been used as building material. In ancient China, sticky rice soup was used as mortar. The mortar was stronger and more water resistant than pure lime mortar, which was one of the greatest technological innovations of the time, and was used to construct tombs, pagodas, and city walls. Some of the structures were even strong enough to shrug off the effects of modern bulldozers and powerful earthquakes. Researchers identified amylopectin, a type of complex carbohydrate found in rice and other starchy foods, as the key ingredient responsible for the mortar's incredible strength. In the near future, food waste could be reprocessed by being baked into a material stronger than concrete. Researchers used vacuum-dried food scraps: orange, cabbage, seaweed, onion, mango, and banana peels. They mixed the powdered food scraps with water and pressed it into a mold at a high temperature, 120 to 300 degrees Fahrenheit, to manufacture the material. The result? Sweet-smelling bricks that are 4 times stronger than concrete and still edible. 1/3 of the global food supply, that's around 1.4 billion tons, gets wasted each year. That's about 31 billion pounds of potential raw materials that could be used to make construction materials. Building bricks with food waste might be applicable when creating self-sustaining colonies, but surviving in space will require some very specific solutions to different problems. On Earth, the atmosphere does a lot to protect us from harmful cosmic radiation cast off from our big, bright, beautiful sun. Outside of our atmosphere, this unfiltered radiation is deadly and unrelenting. But for a developing colony on the Moon or Mars, colonists would need to develop building materials capable of shielding inhabitants from cosmic radiation while out there. There's been research into using regolith or the dust of the moon to create shelters capable of repelling solar radiation. But these structures would also have to be strong enough to protect scientists and other colonists from meteorite impacts. It's no secret that animals were used as labor in the developing world, and their carcasses served a bunch of other functions. Ox blood has been used for mortar in Europe and Asia since ancient times. In China, pig's blood was also used as mortar. But also egg whites were used as a paint binder to paint the world-renowned terracotta warriors in Xi'an. Today, in more modern technology, animals are still used. In other words, your favorite pieces of technology aren't very vegan. LCD screens sometimes contain animal cholesterol. Glue often contains gelatin, which is a protein obtained from boiling animal tissue. Indigenous peoples in the Americas used every part of the animal as both a sign of respect, but also from a very practical standpoint. These animal solutions raises the question, can we use human bodies to do this too? Beyond using lunar dust and food scraps to build space colonies, scientists are developing ways to use the actual blood, sweat, and tears of astronauts to make difficult missions a reality. Serum albumin, which is found in human blood plasma, can be used to bind together Martian or lunar soil to form a substance harder than concrete. Blood would be obtained from plasma extraction, similar to what happens when you donate blood today. Scientists estimate that one person could safely produce enough blood plasma to facilitate the construction of a habitat for one other person every 72 weeks. The more colonists, the more plasma, the more potential habitats. In the movie The Matrix, the human body was used as the energy source by the callous robots running the world. It turns out, in the real world, the amount of energy that can be extracted from your body is pretty tiny. For example, it would take about 3 full days to charge your smartphone. While the heat cast off from the human body isn't enough to power your phone, it could be used to power wearable devices or to heat buildings. We already use crowds of people on Earth to lower heating costs in large public areas. Doing the same in deep space is a practical solution. On the ISS, everything is funded by government space agencies, and astronauts are provided necessary supplies. Nothing is bought and sold. But what about the local economies of future deep space colonies? On a privately owned and operated space colony or deep space business park, it's not that hard to imagine that all the resources necessary to sustain life would get really valuable. With human plasma and wastewater being crucial elements of building a self-sustaining space colony, it's worth considering all the ways in which their intrinsic value will evolve. The corporation that employs you could just be renting you that very valuable drinking water, with the expectation that you're going to return a portion of that water back to be recycled and reused by other colonists. Or maybe small utility companies will emerge to sell future colonists water, recycled from wastewater, human sweat, and urine. Will being a human wastewater reseller be the future's dirtiest but most important job? Would the body heat, sweat, and the urine you cast off working long hours in a space mine or lab be the property of a company that employs you? For the most committed and driven among us, putting our blood, sweat, and tears into our work isn't strange. But we're heading into a future where the literal blood, sweat, and tears of employees has added value. Will we be compensated for our bodily fluid contributions? I mean, a future where sweat equity actually becomes equity is kinda utopian. Or deep space employees could just be signing away a percentage of their body to their employer. How much of one's body ceases to be yours when you leave Earth, and it's crucial to the company mission? I'm just saying, make sure you read the fine print of your future deep space employment contract before launch. For more videos like this, subscribe to this channel right now and hit that notification bell so you don't miss any great content. And look out for CuriosityStream on social media, links in the description.